Hi everyone, welcome back. Today we're going to be talking about exponential growth and decay. And in order to start off with this topic of exponential growth and decay, I want to start off by analyzing, or more specifically in this case, by looking at the definition that we have here for law of natural growth and law of natural decay. The natural growth law says that if we're looking at the change in growth with respect to some variable, in this case t, that we're going to be able to find a certain, let's say, constant times that function itself, the one that's originally changing, and that will then give us a natural growth amount. Okay? Now, looking at natural decay. Since we're looking at a decay here, the coefficient k is then going to be a negative coefficient, and that will tell us that we are looking for a decay factor, or in this case, natural decay. Now, we want to consider one specific function. So let's look at this one specific function where we have y is equal to c times e to the power of kt. Or more specifically, better yet, let's do y of t is equal to c times e to the power of kt. The second notation basically shows that we are able to have y as a function of t, as we have here. Now, if I want to take the derivative here, so if I want to take the derivative, this is an exponential, so c times e to the power of kt, exponential with base e, c is a constant, k is a constant, t is the only variable. So when we use our chain rule to take the derivative, we wound up with the derivative of y is c times k times e to the power of kt. However, if we rearrange this, let's look at this now. Again, I'm rearranging just by commutativity of multiplication. This now says that I have k times some function here, which is denoted as c times e to the power of kt. But this function is just my y of t function, which means my derivative here, y prime of t, is equal to k times y of t. Or we naturally like to just express this as y prime is equal to k times y. We like to use the notation on the left, the one that I am putting a box around, versus the notation that I am circling on the right-hand side. Again, left-hand side is preferred notation, but the right-hand side gives you that process as to what this looks like. Okay, so let's keep going. Let's now start looking at a very, very important theorem here. And I'm going to write it on screen so that we're able to then use it directly. So here goes this theorem. This theorem says that the only solution of the differential equation dy over dt is equal to k times y are the exponential functions functions y of t, which is equal to y evaluated at 0 multiplied by e to the power of kt, as such. So again, this is now beneficial for us to start looking at this process, saying, okay, we now have this differential equation that we said we wanted to look at, and that was by the definitions that are at the top of our screen. That is the initial rate of change that we want to observe, and in turn we want to try to find what is that initial function, y. Well, the theorem says that if you want to find that initial solution, or that only solution, then that solution is just going to be this family of functions, or more specifically, this family of exponential functions. So that's what the theorem is telling us. Now, say that we wanted to work with a specific question that had to deal with, let's say, bacteria growing at an exponential rate. How could we do it? Well, we now have this concept of natural growth or natural decay that we can use to our advantage in order to solve a problem of that sort. So let's go ahead and let's attempt to look at some or one of those. And by internet magic, here is your example. This example says that a common inhabitant of human intestines is the bacterium Escherichia coli, otherwise known as E. coli. A cell of this bacterium in a nutrient broth medium divides into 2 cells every 20 minutes. The initial population of a culture is 50 cells. And now we have an abundance of items to look for. Part A, find the relative growth rate. Part B, find an expression for the number of cells after T hours. Part C, find the number of cells after 6 hours. Part D, find the rate of growth after 6 hours. And then finally, Part E, when will the population reach 1 million cells? So in order to do this, what we're going to do is we're going to start off with what we know and what it is that we are trying to find. And then from there, we can go ahead and make our substitutions for what we need. All right, so let's get started. All right, so part A. Let's work with part A. So I'm going to have part A here, where we want to find the relative growth rate. Now, in order to do this, what I'm going to do is I'm going to start with the equation that we know for having a growth rate of a function. So, using the theorem that we have, if we have the differential equation that gives us exponential growth, then that means that we can be working with the function y of t, which is equal to y at 0 is equal to e to the power of k times t. Now, from the question, we do extract a few items. Number one item that we want to extract is that the cells divide into 2 cells. So this divides into 2 cells every 20 minutes. So every 20 minutes, each cell now divides into 2 cells. And also, we get that the initial population of the culture is 50 cells. That is my function at 0, or at t is equal to 0, is going to be that we have 50 cells. So using this process now, I can say, well, y of t is equal to 50 multiplied by e to the power of kt. Now, if I have a t value, then that's going to work well for me. And I coincidentally have that every 20 minutes, every cell divides into 2 cells. What does that tell me then? Well, that tells me that after the first 20 minutes, the population doubled. So after the first 20 minutes, so at y is equal to 20 minutes, which is 1/3 of an hour. Okay, so 20 minutes is equal to 1/3 of an hour. And that's what I'm using here. At that 20 minutes, all these 50 cells have doubled. So one cell split into two, the next one split into two, the next one split into two, so on and so forth. We did that 50 times, which means we should have 100 cells in that culture. What does this mean now? Well, this means that my 100 cells, here we are, I have 100 cells, and I still have my initial population of 50 multiplied by e to the power of k. We don't know what that k is, that coefficient constant. But we do know t. T we're assuming to be 1/3 because it's 1/3 of an hour. Now remember that coefficient that we don't have yet, k? Well, we can actually solve for k. If I divide by 50 on both sides, I get 2. E to the power of k divided by 3. Taking the natural log of both sides gets me the natural log of 2 is equal to k divided by 3. Multiplying by 3 now gets us that k is equal to 3 times the natural log of 2. But using our properties of logarithms, we now get that k is equal to the natural log of 2 to the power of 3, otherwise known as the natural log of 8. And more specifically, this is your relative growth rate. So the relative growth rate is, and I'm just going to say here, k is equal to the natural log of 8. It's just a constant. There we are. So that looks pretty awesome. It looks pretty good. Now, part B. All right, let's work on part B. Part B is going to go on the right-hand side of your screen. It says, find an expression for the number of cells after t hours. What they mean by find an expression, they mean, see this formula that we wrote down in part A at the very beginning? That's what they mean. Find that and simplify it. So using that equation, y of t is equal to y of 0 times e to the power of kt. But we already know a few of these entries. All right, the first entry, y of 0, that's 50. So we don't need to know more of that. That's 50 multiplied by e to the power of k. Well, what's k in this particular case? K is natural log of 8. So I'm going to insert natural log of 8 multiplied by t. Now, once again, look at this exponent, natural log of 8 times t. Well, since t is multiplying that since t is multiplying the natural log, we can move that t to the argument of, or the exponent of the argument, which will then be e to the power of natural log of 8 to the power of t. But in doing so, e to the power of natural log will now cancel each other out because they are inverse functions of one another, which means the function that we're looking at, y of t, is now 50 times 8 to the power of t. And this is what we want. This is the answer for part B. So we got part A done. Part B is now done. It said find an expression for the number of cells after t hours. And this will now give us the number of cells after any amount of hours that we put in there, after any amount of t hours. Great. Let's check out part C then. So part C then asks us to find the number of cells after 6 hours. So using my newfound equation, y of t is 50 times 8 to the power of t, I'm now going to find out what is that value for 6, because it's after 6 hours. Okay, so that's going to be 50 times 8 to the power of 6. I need my calculator for this, so let's bring that out. So I now get to see that my answer here, according to the calculator, I get that y of 6 is equal to, wow, that's a huge number, 13107 200. Let's put in some commas in here. So it's 13,107,200. That is the number of cells. So I'm going to write that in a summary down here. So there are 13,107,200 cells after 6 hours. Awesome. Now, part D. Well, in part D, what we want to find is the growth rate after 6 hours. So in order to find the growth rate, now we're trying to find a rate, not an amount. So to find a rate, we now need to look at the derivative. So what we're going to do is we're going to quickly look at that derivative to see what we're then able to extract. Now, if you're following along with the rules for derivatives, we have different ways to take these derivatives. Okay, so one of the first items I'm going to look at is going to be looking at this function. Y of t is equal to 50 times e to the power of natural log of 8 times t. And if I look at this particular case to take the derivative, I get y prime is going to equal to 50 times the derivative of this function, which is the function itself, e times the natural log of 8 times t, multiplied by the chain rule, which will be multiplied by the natural log of 8. Okay, in this particular case, again, e to the power natural log of 8, that simplifies, which means I'm left with 50 times the natural log of 8 multiplied by 8 to the power of t. That's pretty cool. So that's using one option. Using another option would be using y of t to be the explicit formula that we found here in part C. Now, if I wanted to find this derivative then, y prime of t, then I know in this particular case, 50 is just a constant, so the 50 stays as is. But then I want to find this derivative, that's just 8 times t, and according to the previous section, 8 to the power of t, finding that derivative is just 8 times 8 to the power of t multiplied by natural log of the base. And look at that, we're left with the exact same derivative. 50 times 8 to the power of t times natural log of 8. So whichever process we take, whichever method we use, it's still going to lead us to the exact same result. And now that question was asking, what is, or to find, the growth rate after 6 hours? So in other words, we want y prime. So y prime after 6 hours, that's going to be 50 times natural log of 8 multiplied by 8 to the power of t, which in this case is going to be 6. We need a calculator for that, so let's go to it. All right, so here we are. I use the same screen to give the answer that we were looking for. So the answer to that's on the left-hand side here of the screen, which means that after those 6 hours, the rate of growth is going to be 27,255,656 bacteria, approximately. So after 6 hours, the rate of growth is 27,255,656 cells per hour. And again, we need to make sure that we put the unit of measurement. The unit of measurement in this particular case is that cells per hour. So that's part D. Now part E, the very last part. So if we go back and if we look at part E says, when will the population reach 1 million cells? So again, I'm going to be using this function that I built, which is 50 times 8 to the power of t. And now I want to figure out when is it going to reach 1 million cells. So 1 million cells is on the left-hand side. On the right-hand side, I want to solve for t. When will that happen? Well, in order to do this, I need to take 1 million divided by 50. And this is equal to 8t. And then we take the logarithmic base. So t is equal to log base 8 of 1 million divided by 50. Okay, so what does that look like then? Well, let's simplify a little bit. Log base 8 of, I believe this should be 200,000 once we divide by 50 is equal to t, which means we'll be able to get the time here. Okay, all I'm going to do is I'm going to put this into my calculator. I'm using log base 8 and I'm using 200,000, and we should get a really nice amount. All right, here we are. My apologies, my math was a little off. 1 million divided by 50 should get us 20,000. My apologies. There we are. Because now if we insert this into the calculator, then now I'm able to get that t is approximately 4.76 hours. So it will take approximately 8 hours to reach 1 million cells. And there you have it. So now we can start talking about different types of examples that still use this exact same concept, that still use this exponential growth or exponential decay, but maybe not so much population-wise. What about temperature-wise, where the temperature changes? What about carbon life, or when we're looking at certain elements? So we're going to go ahead and we're going to do some of those examples. That way, again, we can see that we are still working with the exact same concept. All right, so here's the next example that we're working on. We want a sample of tritium-3. So, sorry, let's start over. A sample of tritium-3 decayed to 94.5% of its original amount after a year. Part A says, what is the half-life of tritium-3? And B, how long would it take the sample to decay to 20% of its original amount? So again, we're still working with exponential growth or exponential decay in this particular case. So anytime that we're working with that, we always go back to the original equation that we started working with. So we always want to go back to this equation, which is y of t is equal to y at 0 times e to the power of kt. And all we have to do now is we have to go through and extract what it is that we're looking at and what it is that we need to solve for. So the first thing that I see that I need to solve for is I need to solve for k. As soon as we know k, in other words, that relative growth rate or relative decay, then we're able to extract and we're able to solve the rest of the equation. So that's my first thought. Now, in order to do this, I see that it says that a sample of tritium-3 decayed to 94.5% of its original amount after a year. So that to me again tells me that we have a year time frame. Okay, so we have 1 year time frame, so I'm going to be using t at 1. Okay, so at t of 1, we have a certain amount. So I'm going to say here to start this off that if I'm looking at a specific amount, I'm just going to call that amount let's just say y of t. Okay, so if we're working with y of t, 94.5% of that original amount, that's going to be 94.5% of the original amount that was, let's say, that this had. So I'm just going to call this A for amount. Okay, it's not looking too bad. So we're going to keep going. Now we have here y of 0, and again this is how much is left in there at a specific time. Well, at a specific time we can say that we started with the original amount, which we'll call A, and then this is going to be e to the power of k times t, but t is 1 because of what we're looking at for the 94% left over. So this is k times 1. Now again, A is just the amount of tritium-3. All right. So again, we don't know the initial amount, and at the end of the day, we don't need to know that initial amount, because what we have here is we have that initial amount will essentially divide itself out, which means we're only going to be left with 0.945 is equal to e to the power of k. And in this particular case, we get that k is equal to the natural log of 0.945. So let's go through and let's figure this out. So again, if you need your graphing, or if you need your scientific calculator, please pull out your scientific calculator at this time. Okay, so what I get from here, I get that this is k. Now I'm not going to approximate k. Negative 0.05, let's say 66. Now I'm not going to use the approximation. Instead, what I'm going to do is I'm going to keep using that process or that specific value, that natural log of 0.945, in order to extract the actual amount that I need. So now I want to work with the function again, because this time it's asking what is the half-life of tritium-3. So half-life means that it was reduced by half. So when we're looking at y of t is equal to y sub 0 for e to the power of kt, the half-life, we're now looking for half of the original amount. Well, if a was the original amount, that's y of 0, and this is e to the power of k, where k is the one that we found, the natural log of 0.945 multiplied by t. Well, what's really nice about this here is going to be that the a's once again cancel out, and we're left with 1/2, and this is going to be 0.945 raised to the power of t, where we can now have that t is equal to, and in this particular case we could do logarithm base 0.945 of 1/2. Okay, that doesn't look that bad. Okay, so logarithm base 0.945. All right, looking good so far. And the logarithm is 1/2. So there we are. So I get that t is approximately 0, or sorry, not 0. I get that t is approximately 12.25. So the answer to the question, the half-life of tritium, so the half-life of tritium-3 is approximately 12.25 years. And there we are. That's part A. So part B is asking how long would it take the sample to decay 20% to 20% of its original amount. So now we want to decay all the way to 20%. Okay, so 20% of the original amount. So again, we're going to do 20% of the original amount, where the original amount is just some value for A. And this is going to be e to the power of k. Remember, k is your constant, and that does not change, and that's a natural log of 0.945 times t. Now again, the the a's are going to cancel, and we're going to be left with 20%. So this is going to be 0.2 is equal to 0.945 to the power of t. Now we could take the natural log of both sides, and that'll lead us to the natural log of 0.2, all right, divided by natural log of 0.945. And this here is going to be my t value. Okay, so again, we can go to our calculator and we go natural log 0.2 divided by the natural log of 0.945. And we should get a really nice number of about 28 years in change. So my approximation here, will say that t is approximately 28.45, which means tritium-3 will take approximately 28.45 years to decay to 20% of its original amount. And that's it. That's all there is to it. Again, it's just working with those same equations that we have. Okay, now we are going to work with one more item. Okay, one more item. That one last item that we are going to work with is going to be Newton's law of cooling. So we want Newton's law of cooling. All right, so let's go through and let's start identifying Newton's law of cooling. Okay, so here we go. I'm going to write down what Newton's law of cooling is, and then we'll go through and we'll start extracting the definitions and these items that we will be needing here. So we're going to have dt divided by dt is equal to k times t minus t sub s. Okay, so this is one of the first items that we work with, and we want to go through and we want to start identifying what it is that we're looking at. Okay, so here I'm going to say that capital T is the temperature of an object at time t. T sub s is the constant surrounding temperature. So in here we have a constant temperature that we look at. Okay, and that's going to be T sub s, temperature of the surroundings. That's going to stay constant. However, there is a temperature that is changing, and that temperature is going to be T, and that is going to be the temperature of an object at any given time. Okay, so what do we then start looking at? Or what do we then want to do? Well, given this, what I want to do is I want to rewrite this a little bit differently. So what I'm going to say here is I'm going to set let y equal T minus T sub s. Okay, the change in the temperature of the object and the surrounding. All right, that's going to be nice. So if I do this, then what I'm looking at here, so I'm going to consider then, oops, let's try this again. Consider the change in y with respect to t. All right, so we're going to consider this value here. Okay, so that's going to mean that we're going to take the change with respect to t for the right-hand side of that equation, which will be the temperature of that object at time t minus the temperature of the surroundings, which will be constant. But by properties of derivatives, since these terms are separated by a subtraction, we can just take the derivative change with respect to one another. However, notice that the derivative of the change in that temperature, that surrounding temperature, that stays constant. Which means, what's the derivative of a constant? Yeah, that's 0. Which means, at this point in time, we actually get here d dt of the temperature of the object at any given point, or at any given time t. Now, why is this important? Well, we actually get from this dy dt is actually equal to dt, d capital T over d sub t. So check that out now. Now this tells me that d capital T divided by dt, well, that's my initial k times t minus t sub s. And well, that's great, but I also made a substitution, right? That substitution then tells me that I now have k times my substitution, which in this case was y. Check that out. So once again, we are left with this equation, this exponential equation that says that the rate of the change in this temperature is going to be equal to k times y, where y is going to be the change in temperature between the object and the surrounding temperature itself. So that's very interesting because, again, still working with Newton's law of cooling, we still arrive at the exact same conclusion that we did previously, that we're still working with an exponential function, whether it be growth or whether it be decay. Awesome. So now we're going to start extracting this into an actual problem. So here we go. We're going to conduct a murder investigation. And we're going to have to find out what's going to happen here. So by internet magic, this problem will then appear in just a few seconds. Here we are, internet magic. The question says that in a murder investigation, the temperature of the corpse was 32.5 degrees Celsius. And that was at 1:30 p.m. And it was 30.3 degrees Celsius an hour later. So 1 hour had elapsed and the body cooled down more. It now cooled down to 30.3 degrees Celsius. Normal body temperature is 37 degrees Celsius. And the temperature of the surroundings was 20 degrees Celsius. What we want to know is, when did the murder take place? Ooh, interesting. Okay, so we have a few things given to us, okay, and we want to hold on to that. All right, so what I'm going to do is I'm going to start working with this equation right up here. Okay, so that's what I want to work with at the very beginning. So let's go with it. I'm going to be using T, that's temperature. All right, so I'm going to extract a few items here. So the first item that I'm going to subtract is going to be the temperature at a certain time. Well, when did we start? We started at 1:30. So temperature at 1:30 p.m. I'm going to say this is T is equal to 0. That's when we're starting that investigation. Okay, so that's one item. I'm also going to extract that the temperature at an hour later, so an hour later would put this at 2:30 p.m. I'm going to say this is T is equal to 1. Now, why am I doing this? Well, I'm doing this for this reason, that the first temperature, the temperature of the object, in this case the body, the temperature of the body at time T is equal to 0 is given by 32.5 degrees. So 32.5 degrees Celsius. The temperature after the 1 hour for that body, so temperature after 1 hour, is given by 30.3 degrees Celsius. Awesome. Now, what I want to do then is I want to then start extracting using Newton's law of cooling. So here, I'm going to start applying Newton's law of cooling. What is this going to tell me? Well, this is going to tell me that I'm going to be using the change in that temperature with respect to time is going to be equal to some constant that doesn't change times the temperature of the object minus the temperature of the surroundings. Okay, so what does this tell us then? Well, this tells us that if I'm going to make the substitution like I did up in the beginning when I was looking at Newton's law of cooling, I'm going to say let y, in this case it's going to be y of t, equal to t minus t sub s. Okay, so if this is going to be the case, then I can then go with y is equal to t minus 20 degrees Celsius, because that's the temperature of the surroundings. And remember, the temperature of the surroundings is always going to be 0. Or sorry, it's always going to be constant. Its derivative is 0. Now, what can I do then once I have this? Well, remember, this is a function. So, more specifically, this is really y of t given by the temperature of the body at time t minus the 20 degrees Celsius. That's going to be the cooling as it's happening. All right. So we're then able to then start extracting. Well, what happens at y is equal to 0? So there's two things happening here. First one is y at 0. In other words, t is equal to 0. That's the body. Temperature of the body at time 0 minus the 20 degrees Celsius. Well, this we kind of already know. The temperature of the body at time 0, that was 32.5. So this is 32.5 degrees Celsius minus 20 degrees Celsius. That's going to be y of 0. What does this get us then? It should get us 12.5 degrees Celsius. Great. Next part. We want to figure out what is that temperature at time 1. So at time 1, when we're working with this, again, this is going to be temperature of the body at time 1, and then minus the 20 degrees Celsius. Well, the temperature at time 1 we already know. And that temperature at time 1 is at 30.3 degrees Celsius, and then minus 20 degrees, which then should get us that 10.3. There we go. 10.3 degrees Celsius. There we are. Looking awesome. All right. Everything's looking good so far. So we can start then extracting a little bit more. And the purpose for this was so that we can start working with this initial equation that we have. Because, remember, at the end of the day, dy dt is equal to k times y. All right? So, if we know this, then we're going to be able to work with this equation very similar to how we worked with last time, in a sense that we can now start talking about k. What is that k value? Okay, so that's what we got to look forward to. And in order to look forward to that, we've now got to find the change. Okay, well, that's not going to be too bad in this particular case. And why is that not going to be too bad? Well, for this particular item, that when we work with dy dt, we get k times y. All right? Now, more specifically, this also implies that I'm working with y of t is equal to y at 0 is equal to k to the power of t. Because remember, this we said was the only solution to that differential equation. So if I can start working with this, which I can now because I now have y of 1 and I have y of 0, I can then start solving k. Now this k value will be the exact same k value because remember, at the end of the day, the derivative of this function is the same as Newton's law of cooling. So we need y of t. Well, what is y of t, or in this case, y at 1? So y at 1 gets us 10.3 degrees. Y at 0 gets us 12.5 degrees. E to the power of k times t, well, t was 1, which means we now have this. So what do we get from all this? Well, we're able to extract then that k is going to be equal to the natural log of 10.3 divided by 12.5. And that's our k value. Which means at the end of the day, we solve for k. That is great. Okay? Awesome. So, now let's see if we can now start finding when did the murder take place. We know how much the temperature of the original human body is. It's about 37 degrees Celsius. So now we then have to investigate that. So what I'm going to do here is I'm going to start using that. Okay, so let me split it here. Now I'm going to be using this in the sense that I now have the k value. So I'm now looking at y of t is equal to y of 0 multiplied by e to the power of k, which in this case is the natural log of 10.3 divided by 12.5 times k. Okay, doesn't look too bad. But again, there's one issue if I need to solve, or sorry, not kt, sorry. Now, there's one issue if I need to solve for t here, because I need to find out what time. What is that change in temperature that we had? Well, the change of temperature here, y of t, this change of temperature is going to be given by the change in temperature that we have, the 37 degrees minus, so 37 degrees minus the 20 degrees. So the left-hand side turns into y of t will be the 37 degrees minus the 20 degrees, which will get us 17. Making all these substitutions, we now get that 17 is equal to y sub 0, which is 12.5. Again, this is on degrees. E to the natural log of this, so this is going to be 10.3 divided by 12.5 raised to the power of t. So I'm going to divide by 12.5, so that's 17 divided by 12.5 is equal to 10.3 divided by 12.5 raised to the power of t. Take the logarithm, and then we get natural log of 17 divided by 12.5 divided by natural log of the base, which is 10.3 divided by 12.5. And that is our t value. Whew, that is rough. Okay, so let's go ahead and let's insert this into the calculator. So I got my calculator out. I got natural log of 17 divided by 12.5, and then I'm going to divide this by another natural log, and this is going to be 10.3 divided by 12.5 once again. And lo and behold, and we get negative 1.588. So I get here that t is approximately negative 1.588. Awesome. 1.588, that is roughly, I'm going to approximate this a little bit more. T is about negative 1.6. So when did the murder take place? Well, what time was the body discovered? Well, the body was discovered, I'd say, at 1:30 p.m. Okay, so now we just need to go negative 1.6 hours before that. So let's convert this into time. Or sorry, let's convert this into hours. So t is approximately negative 1.6 hours. We need minutes. So let's make that conversion. All right, so 1 hour, that's 60 minutes. So I'm going to say here 60 plus 0.6. All right. Whoops. All right, so if I just multiply 1.6 hours by 60, because again, 60 minutes in 1 hour, I should be able to get approximately 96 minutes. Okay. Wow, that's awesome. So the murder took 96 minutes before 1:30 p.m. So if we go back 96 minutes, then we're going to be able to find out what time this murder actually took place. So it took place around, let's say, 11:54, somewhere around there. Wow. The murder took place at approximately 11:56 a.m. Wow, that's crazy. So again, 96 minutes from that 1:30 mark. So that's a little bit over an hour and a half. And wow, that's pretty crazy. So that's pretty crazy. That's about an hour and 36 minutes. Awesome. So there you are. There is the type of question that we see for Newton's law of cooling. And again, you could expect to see a Newton's law of cooling on an exam. Just be very mindful of that. And so I thank you all for joining me, and I will see you all next time to try to wrap up Chapter 6. Till next time.